Hello guys, welcome to our channel of Sciences and Mathematics. Today we are going to solve a problem, and this problem is finding a simpler way, of course, of finding the wavelength, the de Broglie's wavelength for an electron that is under potential difference V. So today our main aim is to try and find a simpler form of the principles which we have learned, of course, in de Broglie's wavelength, so that it can assist us in finding a solution to this particular kind of a problem. So if we find similar problems for this and you have memorized for that case this particular principle, it's going to be very helpful so that it makes the work of calculations simpler. So let's try to see on how we can be able to use that principle in solving this kind of a problem. So this problem requires us to calculate the de Broglie's wavelength, or just to find lambda for an electron raised to a potential of 900 volts. So for that case, we are going to try and figure out which kind of principle we are going to use. And from what we have discussed before, for an electron in that potential difference, its energy is associated, the wavelength associated with its energy is given as lambda over the root of 2me, where E represents its energy. Now someone may ask, how did we come with this particular principle? Just for a quick recap, we said that the de Broglie's wavelength for a particle that is behaving as a wave and a particle at the same time is given as this one. But we said that EV is equals to half mv squared. And then we said that for us, we can simplify this equation by multiplying both sides by 2. Now this one is just maintained. Oh, sorry. So that we have 2EV is equals m squared, mv squared. And then we can multiply both sides by m and try to see which kind of an equation we come up with. So we shall have 2mev is equals m squared v squared. From classical mechanics or classical physics, we know that momentum can be represented as the product of mass times velocity. So 2mev is equals, this is momentum squared, so we shall write p squared. So making momentum the subject of the formula, we can describe this particular momentum of this particle as the root of 2mev. Okay, great. So for that case, let's do a substitution for momentum. We shall have de Broglie's wavelength as Planck's constant divided by, we do a substitution for momentum, 2mev. So that is the principle that we had mentioned earlier that we are going to apply in this particular equation. So we shall look for a simpler form for that particular equation, because some of its parts that we have been given there are the known constants. So let's do this and write lambda is equals Planck's constant. We know the value is 6.626, or in that case, it is always encouraged that you use the figure or the constant that you have been given, or some other problems may be accompanied by a constant, so it's just always encouraged that you normally stick to what you have been given. So for that case, we're going to use this, and then divided by the root of 2 times mass of the electron, 9.11 times 10 raised to power negative 31 kgs, times E represents the charge. The combination of these two represents the energy of that electron in its potential difference V. So in that case, we shall have A representing the charge, 1.6 times 10 raised to power negative 19 coulombs, that's the charge of an electron, times the V, which is the potential. So doing our calculation for this yields lambda as 12.27 times 10 raised to power negative 10 divided by the root of V meters. So solving this for this equation gives us lambda is equals 12.2 times 12.27 times 10 raised to power negative 10 meters. So in the multiples of units, this one represents what we call an angstrom. So for that case, we can represent lambda to be equivalent to 12.27 divided by the root of V angstroms. So this is a simpler form for our formula that we have written, of course, that contained h, the root of 2m ev, can be rewritten as that particular formula. So we are going to use this particular formula in finding the solution to this particular problem, and the units are going to be in angstroms. So let's calculate the de Broglie's equation for this particular problem using that equation of lambda equals 12.27 over the root of V angstroms. So we substitute for V, since we know that V is equals to 900, which is 12.27 divided by the root of 900 angstroms, which is 12.27 divided by 30, of course that will be an absolute value, angstroms. So if we do a calculation for this, we can simplify, and just a minute as we do that one. Let me open my calculator. So that is 12.27 divided by 30. It will be 0.409 angstroms. So our lambda, using that particular concept of the principle, or the principle which has been simplified, yields as 0.409 angstroms. So for that case, thank you guys. This is one of the ways in which we are going to simplify some of the formula that we come across, so that it is easier for us to memorize, or when we come across such a kind of problems, we are able to solve them with ease. So thank you for the day. Welcome. God bless you. Bye.